Real estate investment practice problem using OneNote. Amortization schedule, where we change the payment and look at the impact on the loan term, holding everything else constant. Get ready because we're about to raise the stakes with real estate. Here we are in OneNote. If you have access to OneNote, would like to follow along, you're not required to, but if would like to, we're in the icon on the left-hand side, the Practice Problems tab in the 4160 Amortization Schedule PMT Change Impact on Loan Term tab. Also note, when using OneNote, take a look at the Immersive Reader tool. Our presentations will also be in the text area, same name, same number, but with transcripts. Transcripts that can be translated into multiple different languages and either listened to or read in them. Closing the icon, we got our information up top, calculations on down below. Remember that as we have seen in prior presentations, prior practice problems, the normal setup you have when thinking about an amortization table is that you have all the information up top here that will vary, and then you'll be calculating the payment item. However, it can be useful to reverse that. In our case, we're going to be seeing what the payment item is, populating the payment item, and then looking at the impact on one of the variables up top, holding everything else constant. In this case, this time, looking at the terms, in other words, the years of the payment. Now, we do this calculation in Excel if you would like to work it through in the practice problem there, although we'll be formatting, so it'll be a bit longer there to do. And or if this is relevant, you can use the Excel worksheet to populate and use for your decision-making processes in the answer key worksheet as well. Now, note that as we change this item, the years, we have a couple other complexities that come into play. One, the years normally, when we think about the loan term, you can't usually just pick any kind of year that you would like. Meaning, if I choose a payment down here of $2,000 and then I have everything else constant up top in terms of the loan amount and the rate, and I calculate the number of years, I might get some odd years, meaning it's not going to be even in years or months. And that's not typically how it works. And when you're getting a loan, usually when you're thinking about a home loan, they have specific intervals such as 30-year or 15-year or something like that. So what we would like to do, we're going to try to round this a little bit so we get some even years or years in increments of fives. That'll give us one added level of complexity. The other level of complexity when you're looking at this as the changing factor is that when we create the amortization schedule, we're going to have a different number of periods, meaning 120 to 360 and so on. And that means that we got to make sure that we populate our Excel worksheet so it can accommodate the changing of the schedule sizes. So we'll look at those two little twists in here as well. So our data up top, we got the home value of the $200,000 we're going to be working with, 20% down. That's going to stay constant. That means the down payment's going to be $40,000, and the loan amount is going to be the $200,000 minus the $40,000, or $160,000. Then we're going to have the number of periods, the thing that's going to change with a formula in alignment with the change down here that we put into the payment item. The rate is going to be held constant at the 5%. Now we're going to have these two payment items down here because this is going to be part of that twist, part of that problem with the loan terms that we would like to have to be in intervals of 5. So what we're going to do here is I'm going to have the payment item here. We're going to set the payment item here. This is where we would just hard code what we think we can afford. We're going to say I can afford $2,000 a month. We're going to put the payment item here. Then we're going to hold everything else constant, rate, loan amount, and so on. But then the loan term is the item that's going to change. Now, what we would like to do is have the loan term calculate so that it will change and round to periods of 5 years in increments of 5, because that's more likely to be a loan that you might actually be able to find on those terms. And then because we rounded it, we will recalculate the payment down here based on the actual rounded loan term, which should be lower than the payment that we originally put in there, because we're going to round it in such a way that we'll always see a lower payment. Okay, let's see how this will work. We're going to put the 2,000, so we'll type in 2,000. We're going to use the years to try to calculate the term. Now, if I was going to use the term calculation, note that usually in prior presentations we have calculated the payment amount. one of the arguments in the payment amount is called the NPER, you'll notice. And it's right here in the payment calculation, that NPER, that's the number of periods. The number of periods then, if we solve for the number of periods, will give us the number of periods that we're looking for. Couple kind of quirks here, however, is that the periods are usually represented, the periods we're working with are months. We want to see the periods in years, and then we want to round it so that we're going to have increments of 5. So let's see how that might work. A little bit added complexity here. If we didn't have this as our rounding function up top, ignore that for now. Pretend this whole first part wasn't there. If I just said equals NPER to get the number of periods, and then calculate to the number of periods, it would be the rate, which would be that 5%. We would divide it by 12 to get the monthly rate, comma, the payment amount, which needs to be negative, so make sure you put a negative in this one, and picking up the payment, which is going to be the $2,000 that we have in the second payment that we would have hard-coded in there, comma, then the present value is going to give us the loan amount. That's going to be the $160,000 in this case. If we just stopped there and had just this portion here to here, that would then give us the number of periods, but it would be giving it in months. And what we want to have it is in years. So then that's going to be the 12 that we're going to pick this up then in years that we would like. So we divide by 12 to take the monthly amount and then divide by 12 to get the yearly amount. So if we did this whole from here to here, that would give us the yearly amount, but we would end up with a number that was not rounded nicely, so we wouldn't be able to find a loan, say if it was like 11.534 years or something like that. So we would like to round it. Now we could round it using just a round function, which would be equal round, and that would round it to you could round it to the nearest whole decimal, or you could round it to factors of 10 if you wanted to round up, which might give you the idea that I'm going to always have a round up rather than rounding down. Then you can use a round up and round it either to the year or in increments of 10. But what we would like to have is to have it rounded to increments of 5 in essence. So we can't really use the rounding function. Instead, we're going to put in front this function, which will basically round it to kind of increments of 5. I'm going to call it rounding to increments of 5. It's going to round up all the time so that we always end up with a payment that will be actually lower than our payment down here because we're going to be rounding up, extending the period out further. So for that, we're going to put in front of this NPER, this formula ceiling.math, which is kind of a funny name, but ceiling.math, and then we're going to embed the NPR, which is going to be the first argument of that function. And then you got to put a comma, and then we're going to put the argument, which is going to be -5. -5 meaning we don't want decimals. We want that's for positive numbers, so we want -5, and that will give us the rounding to increments of 5. So this one then is going to round up to 10. That's what that's going to be. I know that's a kind of a complex formula. If you want to look at that in more depth, you can take a look at it in Excel. We just went a little bit further on that one. Now, if I rounded it, then this payment amount is actually not correct because now we've rounded it up top. So if we now say that's 10 years, 10 times 12 being 120, now we're going to recalculate the payment based on the rounded amount of periods, which is 120 months, which is our standard payment calculation, equals, I'm going to say negative payment to flip the sign, rate 5% divided by 12 for the monthly rate, comma, number of periods is now going to be that either 10 times 12, or we calculated that to be the 120, which we're picking up here, comma, the present value then, loan amount, is going to be the 160. That means that the actual payment is going to be the $1,697.05. So the way this works, we said, okay, we can afford $2,000, so we're going to put $2,000 in. It's going to round it to increments of 5, which in this case is 10 years, and then give us the payment amount, which should always be less than, and therefore within our budget, than the amount that we actually calculated because we're rounding it up to the 5 increment. Okay, so that's going to be the idea. Now, once we have that, we could still calculate the total payments, obviously, which would simply be now the 1697.05 times now 120 periods, not 360, 120. That's going to be the 203,646. And if I subtract out then the loan amount, 160,000, that would give us the 43,646 in terms of the total interest. We might then want a side-by-side calculation saying, well, what if I took my payments from 800 and increased it by increments of 100 and kept everything else constant, rate and loan amount, and then just looked at the change in the years here in terms of the terms? What would that look like? Now, this first cell, the years cell, is calculating it without this rounding function, without this first point. So we could see this function a little bit more easily. And then the second column is going to round it to increments of 5, that being our ceiling.math function, the embedded part we did here. So we'll do it in a two-part method so you can kind of see these formulas a little bit more easily. So for this first one, if I had 800 on the payment, we would have the equals NPER, number of periods, is going to be our unknown. Then we're going to take brackets, the rate's going to be that 5%. We're going to make it an absolute reference, so when I copy it down, it'll not moved down. We're going to have $ before the B and 7, absolute, divided by 12 to get the monthly amount, comma, the payment amount. The payment amount now is going to be that $800. It's got to be -2, by the way, that 800. That one is not absolute here because when we copy it down, we want this cell reference to move down to the 900. Then we have comma, the present value. The present value is going to be the loan amount, which is this 160. It's absolute because it's coming from our data, $ before the B and the 4, so that when we copy it down, that one does not move down. And we're going to take that entire thing, which would give us the amount in terms of months, and divide it by 12, which would give us the amount in terms of years. This one then coming to about 35.91 years. Now, again, there is no such thing as a 35-point-some year typically when you're talking about a home. Usually, and there's not usually something like a 36-year either. That's not usually a thing. There might be items like in increments of 5 that would be more likely to be available. Therefore, we're going to use the rounding function, or in other words, the ceiling.math function to try to kind of round it to increments of 5 is what we're going to do. And the ceiling means it's going to basically round up. So it's kind of like a round up function to increments of 5. So it doesn't round down, because if I round down, then I'm going to end up sometimes with a payment that will be higher than the amount I typed in here. And I'm going to try to result in a payment that would also always be lower than the amount we typed in there. So if we enter the ceiling, meaning once I round it and I calculate the payment, I want the payment to be equal or lower. Okay. So it's going to be equal to the ceiling.math, and then we're going to say brackets. We're going to then pick up this number, the 35.91, and then comma -5 is going to be what we need in order to tell it to round it to increments of 5, and it rounds it up to 40. So if I had 900, the years, same formula here, would be the rate, same number because we copied it down, divided by 12, comma, payment. This one changed from 16 to 17. Because we copied it down, that being now the 900, comma, then the present value, the loan amount, it absolute has not changed because of the $, divided by 12. That one gives us the 27.05, which if we round up to increments of 5 would be 30. The next one gave us the 22.05. If we had a $1,000 payment, we rounded up to 25. The 1,100 gave us the 18.67 years, rounding up to 20. This one, for example, 1,300 gave us the 14.41, which rounds up to 15. This one, for example, gives us the 1,700, which is the payment was 1,700, gives us the 9.98 years, which we round up to 10 years. Once we have that information, then we can do our similar kind of calculations down. So once we have the years, we can calculate the amortization table. Now, so this one had 2,000 on the payment, which calculated out to be 10 years, having everything else constant, or 120 months. And then the actual payment was the 1,697 after we rounded the years. That's what we're actually using in the amortization table. Now, the other complexity is that we have this table that's long enough to accommodate, say, 40 years down here, but it's going to stop after 10. So we could see it goes to 0 at 10. So it looks correct. I can't use the totals at the bottom of this table because it's going to continue on with those negative numbers. But I already have the totals right here, so that shouldn't be a problem. And if I want to do projections into the future, then it might be easier to use our pivot tables in order to get a year-by-year breakout. So that it should still work for us, even though that we got this kind of ugly long table and this bottom half of it is irrelevant with the negative numbers down here. It's going all the way down to 40 periods now to accommodate this time 40-year loan, if that's something that we would be considering. We can also slice the table up using our slicer, looking at it year by year. Here's the totals for the payments, the interest, the loan reduction, and loan balance for year 1. Here's year 4. So we got that nice slicer capability, which is in essence a filter. We can, of course, also add the pivot table. I'm not going to go how to add it in detail here because we've seen that in prior presentations. You can go back there if you want to take a look at it. But in essence, if we create a pivot table, that's an easy way for us to get the breakout from 1 to however many periods, noting here again that if we pivot it by years, it's still going to show us 40 years because that's how long the table is, even though it stops after 10 years in this case, because that happens to be the loan term. But we need to be able to accommodate anything from 5 to 40 years if that's going to be the range we're looking at in terms of terms. So if we make some changes here, if I said 800, for example, in the payment amount, we'll type in 800 into this worksheet, and then it's going to say, okay, that's going to give us a rounded up in increment of 5's loan term, holding everything else constant of 40, which is higher than the actual amount because it rounded it up in increments of 5. And that means that the actual payment amount should be something less than what we typed in there, in this case, the 77151, which is the amount that should be used when creating the amortization table. And then if we sum these items up, we're going to get and refresh our pivot table. We can see this on a year-by-year breakout. So now we're looking at the pivot table year by year instead of payment by payment. Notice we got 480 payments, 40 year. This goes all the way down to 40 years now. Now every column is populated because this is our longest loan term at the 40 years. If we were to change this, say, to 1,200, we can imagine typing in 1,200 or taking that from our drop down if we made a fancy drop down. And then we're going to say, okay, that means everything else held constant. The years are going to calculate to some amount that is then rounded up to increments of 5 of 20 years. That 20 years, because it's rounded up, is going to result in an actual payment amount that should be equal to or lower than the amount we typed in this case, $1,055.93. That amount then being used to populate the amortization table. This then being the pivot table, which we can refresh and see this information on a year-by-year basis, this time 20 years. So you can see at 20, it goes down to 0 here. And then once again, we have the bottom of this table that's not relevant for us, but gives us the information we need. And if we want to copy and paste it into some other table in order to use it for comparison purposes, we have what we need to do so. Let's do one more. Let's say the payment was at 1,600, which we typed in, so we could afford 1,600. Keeping everything else equal, the loan's going to calculate and then round up to increments of 5 of 15 years. 15 being higher than the actual years if there was no rounding means that the actual payments are something equal to or less than what we typed in this case, 1,265.27, which that number would be used to create the amortization table. And then we can refresh the pivot table, which we're seeing on the right-hand side, which can give us the breakout on a year-by-year basis. Once again, the loan term stopping at 10 years, bringing it down to 0. The table continuing on with useless data past that point, but giving us the information we need to possibly copy and paste for further analysis for something like this. For example, if we wanted to take those 3 pivot tables that we looked at for payments of 800, remember, these are approximate payments of 800, 1,200, and 1,600, which were then calculating the terms based on that and rounding down the payment based on the actual, well, rounding up the term and then calculating the actual payment based on the term. So if we said $800, then it basically took the term, rounded up the term, and then gave us the actual payment, which would be less than the $800. And that then we can see that's the one that resulted in that 40-year item, and these are the interest payments over the 40-year. If we had the $1,200 that we think we could afford, then we entered that into the system. It then rounded the period up to the increments of 5, which would result in an actual payment of something less than $1,200 as we saw, and we could see the loan term stops down here at 20. So for this one, when I copied it from the pivot table, for example, I just copied down to column 20 and stopped all this useless data below. Don't need it anymore, and we can pick up what we need. This one, the 1,600, then would do the same thing. That resulted in a 15-year amount. We can also do that for the loan balances as we've seen in the past, looking at where we stand in terms of the loan balances. Same kind of concept, so we can do some comparisons as to where we would stand in terms of loan balances at the end of each of these basic years, comparing and contrasting these different terms. So once again, we work through this practice problem in Excel if you want to work on any of these tools, and or if you think this would be a useful worksheet to just make your analysis with, we have the answer key as well that you can use for that purpose.